Hi, and welcome to this section of the Advanced Calculus 2 tutor. And in this section, we're going to continue our foundation of sequences and series. And in this section, we're going to talk about the topic of introduction to series. What is a series? Okay. The good news is it picks up right where the topic of sequences ended. It's very much related to the sequence concept that we did right in the last section. Obviously, it's new material, so there's some new things to learn. But I think once you have that foundation, you're going to do just fine here, okay? So the short story here is, and one thing I'm going to apologize to you a little bit ahead of time is, as I teach this section here, unfortunately, I can't dive into the examples really soon. Because if I do that, you're going to get confused and you're going to have to apply the theorems without me teaching you the theorems, and that's not going to be very productive. So what we're going to do here is I'm going to have some front-loaded work a little bit to give you some theorems that you're going to see in your textbook on the first few pages of the chapter dealing with the sequences, with the series, okay? And I'm going to show those to you and hopefully try to explain them to you in a different way that makes it easier to understand, easier to remember. And then we're going to dive into the problems and apply them, okay? So we're going to have to get some groundwork done first is all I'm really trying to say. So what is a series, okay? Remember back to the sequence we did just a minute ago. The sequence was just a list of numbers. 1, 2, 3, 4, whatever. 1/2, 1/4, 1/8, doesn't matter. Numbers separated by a comma, that's what the sequence was, okay? The series is when you begin to add those numbers up, okay? That is really it. I mean, that's all you're doing. You're adding those things up. So, whereas before, you may have 1/2, 1/4, 1/8, 1/16, whatever, a sequence. Here in the series, you're going to be adding up those elements. And you're going to be arriving at some sum, okay? And that sum is going to be something we're going to be very interested in. Because remember, just think conceptually. I'm going to give you a big 100,000-foot overview of this section. Remember in the sequences section, the one we just did just a minute ago, okay? We were looking at the behavior of the elements of the sequence as we looked at terms that go off close to infinity. As we go bigger and bigger and bigger, do they go up? Do they blow up and get really large and just go to infinity? Some of them do. Do they approach 0? Do they converge to a number? Do they approach 0? Okay? And so we're taking limits here. Okay? Now just think about it for a second. If you're going to add up the elements of those sequences, and let's just say the original sequence you had, the original sequence blew up to infinity. All the numbers, the actual elements of the sequence got bigger and bigger and bigger. So if you add them up, if you approach infinity and you begin to add up an infinite number of these things that are getting bigger, well, obviously your sum is going to get bigger and bigger and bigger. It's going to diverge. It's going to go bigger and bigger as well. But, and just stretch your brain here with me for a second, if you have the elements of the sequence that happen to approach 0 fast enough, okay, if you have elements that go 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1/128, whatever, they get smaller and smaller and smaller as you approach infinity, then it might be possible for you to actually add up an infinite number of things. But because the elements are getting smaller and smaller and smaller, I might actually have a series, which is the summation, converge. That's what we're going to be interested in this section. That's the motivation. We're going to be interested in looking at these series, which are not the elements, it's the sum of the elements, and we're going to be trying to find out if those sums can converge or not. That's exactly what we're going to be doing in this section and the next several sections, okay? So put your thinking cap on. We're going to go to some different territory here. It's not going to be too hard, but we're going to have to go through some theorems first. So that's our motivation. Let's recap a little bit. If we have the elements A1, A2, A3, these are elements. A4, ... AN, these are just elements in a sequence. Okay? If we begin to add these things up, okay, remember, this could be an infinite number of things because the sequence goes on to infinity usually. But if we begin to add these things up, then we say we have a series. And that would be something like A1 plus A2 plus A3 plus A4 plus ... plus A sub n, whatever the nth term is. And again, I may have an infinite number of terms, so I'm adding up an infinite number of things, okay? And by the way, you would think that if you add up an infinite number of things, you're always going to get infinity, right? Because you're adding an infinite number of things up, right? Well, that's not always the case. So you're going to have to stretch your mind a little bit because it is weird and it's not intuitive at first. But what I guess I'm going to give away a little bit here and give you the punchline a little bit. When the elements of the sequence actually approach 0 at a fast enough rate, even though you add an infinite number of them up, you may actually converge in your solution. And that's hard to wrap your brain around, so just think about that as we as we go on with the lecture here, okay? So, if I'm adding up the terms in the sequence, I'm going to get a summation like this. So let's go ahead and write it in summation notation. So you might see it written as a sigma, right? Which you should remember is your summation. From n is equal to 1, let's say to infinity, if I have an infinite number of terms, over a sub n. So whereas before we just had the a sub n here, and that was just a listing of the elements, this summation is actually adding up these elements from 1 to infinity. So this means that I'm literally adding up an infinite number of numbers. I never stop. I punch numbers in my calculator till the sun explodes and the universe ends. I'm still punching numbers in, okay? And that's an infinite series, that's what it's called, okay? So sometimes you write it like this. Sometimes you write it just simply as the summation over a sub n, and it's implied that it's going on to infinity. Most of the time in calculus, we're only going to be interested in series and sequences that go on to infinity. Okay, so we call it an infinite series. Okay? And a lot of times we don't even use the word infinite because you'll be dealing with infinity so much, you'll just usually call it a series. So in your book, when you see a chapter on series converges, series diverges, whatever, you're talking about infinite series usually, okay? So let's define some terminology as we go on in our study of the infinite series and how it behaves. You can define, okay, something that sounds complicated, but it's not complicated at all. You can define something called a partial sum. And I'm actually going to call it the nth partial sum. All right, so let me just show you what that's equal to. The nth partial sum would be defined as follows. I think the easiest way to do it is to switch colors and just show you by a quick little example here, by analogy. The first partial sum, s sub 1, s means sum, it's a partial sum. I'll show you why it's partial in a second. Of this sequence here is going to be a sub 1. It's just the first element because it's just the first thing here. I haven't actually done anything. The second partial sum is a1 plus a2. So I'm just adding up the first two elements in the original sequence. The third partial sum, you might guess, is a1 plus a2 plus a3. Notice I don't have any dots anywhere. I mean, this is literally the third partial sum is three things added together, the first three things. And then just for grins, I'll put the fourth one, a1 plus a2 plus a3 plus a4, right? So for the fourth partial sum, it's like this. And that's why, by the way, they're called partial sums, because the sum of the series, the entire sum of the series, which is usually an infinite series, is an infinite sum, okay? So that's usually the summation symbol that you'll see is almost always going to be dealing with an infinite sum of terms in the sequence, okay? But we're not talking about that yet. We're getting there. We're building the motivation and the rationale, but we're not there yet. So they'll define this thing in the books called partial sum, which is just up to that point in the sequence, if I only add that many things together, I have a partial sum. I'm only summing partially up till the fourth element, the third element, the second element, and the first element. You see now why it's just the first element there. Okay, so for the first partial sum, we're adding the first number. Second, we're adding the first two elements. Third, we're adding the first three, and fourth, we're adding that. Okay, so what we can say, here is, and this is kind of crucial, so I'm actually going to write the words out here. These partial sums form a new sequence. They form a new sequence, okay? And that sequence is going to be S1, comma, S2, comma, S3, comma, S4, comma, dot, 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 Sn, and that would be my sequence, okay? So why am I doing this? Remember, originally what we're interested in doing is we're interested in adding all of them together. Okay, we're adding all of the elements in the sequence together, and we're trying to find out what this thing adds up to. Most of the time it's going to go on to infinity, but sometimes I'm giving you a little bit of the answer here. It's not going to go to infinity, and we'll show you why. Okay, so in order to get there mathematically, they define these things called partial sums and say, okay, look, now we're going to just add the first element to nothing, right? Now we're going to add the first two elements. Now we're going to add the first three elements. Now we're going to add the first four elements. And these partial sums, if you write them in a list like this, we're going to say that that's a new sequence of numbers. This is exactly what a sequence is. It's a number with another number, and another number, and another number, followed by a comma in the curly braces, and that is a sequence, okay? So if I were to look at how these partial sums behave as n goes to infinity, then I would know how the entire sum of the elements behave, right? Because here I'm adding one thing together, and then I'm adding 2 elements together, 3 elements, 4 elements, and as I go out here, I'm adding all of the elements together. I'm adding all of the elements together, and that's what I'm trying to get to. So I'm building mathematical rationale here, you see? So if I were to actually do this in my calculator and write down numbers here for the partial sums, and if I were to plot them on the plot just like we did in the last section, and find out how they behave as n goes to infinity, remember, when n goes to infinity in this case, since I'm talking about partial sums, what I'm arriving at is the entire series, the entire thing, all the elements added together, which is exactly what I'm trying to find. So if I look at the behavior of this list of numbers, I will find out if this sum converges or not, okay? I will find out if that sum converges or not. So what I'm going to say in words is the following. It's very important. If these elements here, which is another sequence, which are the sequence of partial sums, if the sequence of partial sums approaches some limit L, whatever L is, it's a number, if it approaches an actual limit, not infinity, right, then we say that the series converges. We say that the series, the original series that I'm trying to find here, which is the sum of all of these things added together, we say it converges to that limit L. Okay, which is the sum that we're interested in, otherwise it diverges. So we're building a little bit of rationale. We haven't gotten into any examples yet, but what we're saying is very, I think, easy to understand in the context here, and that is that we have these elements of a sequence. They're just numbers. We're really curious if we can add an infinite number of them up and get something other than infinity. Okay, so what we do is we start adding up in chunks. We add the first 2, and then the first 3, and then the first 4, and then the first 5, and then the first 6, right? And then we're getting these partial sums, which are these little bitty additions of more and more and more terms. And then we look at how that behaves. If those partial sums approach some limit, maybe they approach 1, maybe they approach 2, maybe they approach 25, then we say that the original infinite series converges to that limit. And if those partial sums go off to infinity and just explode because we're adding up infinite number of big numbers together, then those partial sums will get bigger and bigger and bigger and not converge to anything, and then we will say that the series diverges, okay? So we're going to be talking about questioning if the series converges or not. Just like in the last section, we were looking at if the sequence converges or not. The difference between the two, and I'll say this one thing and we'll move on, is that in the sequences in the last section, we were just looking at the numbers to see if the numbers converge to a limit or not. Here, we're looking at the sum, the partial sums of adding up more and more and more of these elements of the sequence to see if the sum converges or not. And that's the difference. That's what the topic of series deals with, okay? That's what the topic of series deals with. So, I'm going to write some things down because I think you're going to see them in your book. And I want to just make it totally bulletproof, because if you don't get this stuff, then the other sections are just not going to make any sense, okay? So, to summarize what we just said below in words, if you're given a series, okay, if you're given a series, and that series is a summation, because we said that's what these series things are, from 1 to infinity of a sub n. And that's going to be equal to, don't forget, it's just adding 1 plus a2 plus a3 plus dot, 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 all the way up to a sub n, okay? Then we have a series that's equal to the addition of all of the elements in the sequence. Then we define Sn, which denotes the ith, or the nth, I guess I really should say, partial sum. I'm actually going to change this because I don't want to get you confused. The nth partial sum, which is adding up the first n terms in that sequence. And what we're going to say here is that S sub n denotes the nth partial sum of this guy, denoted as follows. S sub n is the summation from 1 to n, because it's the nth partial sum, okay, of the elements here, a sub I. So you'd have a sub 1, a sub 2, plus a sub 3, plus a sub 4, all the way up to whatever the nth partial sum is. So I can find the first partial sum, the second partial sum, the third partial sum. Each time I'm only adding up that many elements of the sequence. That's all it's saying here. This is big fancy math talk. That's all it's saying. I'm adding up the first n elements, okay? So here's the series. It's adding all of them up to infinity. I can denote the nth partial sum, which only goes up to, you know, whatever n I'm looking at, okay? Then if these partial sums converge as you add more and more terms, then the series converges. Then the series converges, okay? So let me make sure you understand that, okay? You have these partial sums, and they're defined as only adding up the first n number of terms in the sequence. As you go bigger and bigger in n, the s sub n, you're adding up more and more terms, okay? If these partial sums, which are this mini summations of this guy, converge, which means they just approach an actual number, as you start to add more and more and more terms, if they start to level off and converge, then we say that the series converges to that number, okay? So what we're saying mathematically is the sum as n goes to 1 to infinity of a sub n is equal to s, okay? S is the sum. So what we're saying here is that the series, the entire series of all the elements, then converge to the sum s. S sub n is the partial sum. It's only the sum up to a certain point in the sequence. Big S here is the whole enchilada. It's how all of them add up and how all of them sum together to give you some number. Okay? So this is basically the same thing as saying a sub 1 plus a sub 2 plus dot 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 plus a sub n is equal to big fat S. That's all it's saying. You add these things together, you get a number. That's what S is equal to. Okay? And we say it converges to S, then we say the summation, which is the series, converges to S, we converges to S, and S is the sum of the series, okay? Otherwise, it diverges. Now, we're going to review the bidding here because this is actually very important stuff. Given a series, which is the summation of all of the elements, all of the infinite number of elements in a sequence, 1 goes to infinity of the elements here, you add them all up, okay? That's what we're saying a series is. We define the nth partial sum of that series, and we say, okay, now we're going to only add up the first 2, the first 3, the first 4, the first 5 elements in that sequence, and we're going to get different numbers as we do that, and we're going to get partial sums, okay? If these partial sums converge, in other words, they begin to level off and approach a number, as you add more and more and more and more terms, then we say that the entire series converges to the number s. The number s is what we say that series converges to. It converges to the number s. Otherwise, if it doesn't approach a number, the series diverges. So all of your problems are going to basically say, does the series converge or not? If the series does converge, what does it converge to? In other words, what number does it add up to? And if it diverges, well, then obviously it diverges. Okay, now there is one type of series that you really need to be familiar with, and it's called the geometric series, because it comes up over and over again. It would be worth your time to really understand this very well, because as you get on into the other sections, you'll be haunted by the geometric series, and they'll expect you to really know it, and it's very useful to be able to solve the problem. So let's talk about the geometric series. Geometric series. Okay, it has a special form. That's all it is. It has a special form. Once you recognize the form, then you just be able to use it. Okay, so what it looks like is the following: summation as n goes from 1 to infinity of a times r to the n minus 1. Okay, now notice this looks quite a bit like some of the series that we were talking about before, when I was telling you that sometimes the elements when it converges when r goes to 0, when r is less than 1. And it diverges when r is greater than 1, and in fact it's very, very similar, okay? So this is sort of the general case here, because you have an arbitrary number a out in front times r, which you'll see r is very important, and then you have n minus 1. So what does this look like if you were to write it out? This kind of looks a little bit intimidating. What would it look like if you write it out, okay? It would be something like a plus ar plus ar squared plus dot dot dot. AR to the third, AR to the fourth, AR to the fifth, and so on. Notice when n is equal to 1, I have 1 minus 1, which is 0, so this disappears, so I have a. And then n is equal to 2, then r is 1, n is equal to 3, then that means r squared, and so on. So you see a plus ar squared plus ar cubed, whatever. It's called geometric, by the way, just so you know, because the adjacent elements here in the sequence that you're adding together, if you were to divide these two, ar divided by a, you'll get r. if you look at these two, if you take AR squared divided by AR, you're also going to get R. And if you take the next one, AR cubed, and divide it by AR squared, you're still going to get R. So what you have here is you have a sequence you're adding together in this geometric series, okay? And the adjacent elements in the sequence differ. Well, I shouldn't say they differ. They have a constant factor between them. They basically have a constant factor between them, and that constant factor is R. The ratio of the adjacent elements is a constant. That's what I'm trying to say, and that's why they call it geometric, okay? So it's a very specific type of series here. But the bottom line is you have a number, it's just a number, and then you have a number raised to a power here. So what you'd like to know is when is this thing going to converge and when is it going to diverge, okay? And it's going to be very similar to what we talked about a little bit earlier, okay? This series is convergent if the absolute value of R is less than 1, which, by the way, if that looks a little bit foreign to you, all this means is -1, R is between -1 and 1. That's all this absolute value is less than R business. That just means R is between -1 and 1. That's exactly what it means here, okay? All right, because look, by the way, if you put -1 in here, or if you put some negative number in here, you take the absolute value, it is going to be equal to less than 1. So this is a shorthand way of writing this, okay? So this series is convergent if R, the absolute value, if it's less than 1, in other words, R is between -1 and 1, just like before, and its sum, so the actual thing that it adds up to is equal to, I'll just write it like this, sum n is equal to 1 to infinity of a times r to the n minus 1. This is just the series. I'm writing it over again, is equal to a times 1 minus r. Okay? And obviously it's only valid for absolute value of r less than 1, which just means r is between -1 and +1. So this is very important, okay? And let me write one more thing down and we'll go over the whole thing. If r is greater than or equal to 1, the series diverges. The series diverges. So this is an important thing here. I need you to really remember that, okay? So what we're doing here is we're saying we have a geometric series, very specific form. Number times some r to the n minus 1. It's going to look like this when you write it all down, which means the adjacent terms have a constant multiplier between them. In this case, it's r, okay? It converges if the absolute value of r is less than 1, which means r is a fraction. R is a decimal. That's all it means. And it converges for the same reason, because if you basically what it's saying is, in this case, if r is between -1 and +1, if you keep multiplying it by r, which is what r to the n minus 1 is going to do, is as you start picking bigger and bigger n's, you're going to be multiplying by r for every one of these things, and these terms are going to approach 0. Okay, the terms are going to approach 0, so that's why it converges. And furthermore, not only does it tell you if this converges, it tells you that the actual sum that this infinite number of things add up to is a over r, 1 minus r. So that's pretty fantastic when you think about it. I didn't derive this. This is something that you know is you could derive it, but you know, it isn't all that terribly useful to be able to prove that. But it is very important for you to be able to use it. So if you have 2 times r to the n minus 1 and you have a sum here, and you know what r is, then all you have to do is put a over 1 minus r, and that tells you what that actual thing converges to. Even though you're adding an infinite number of things up, you actually know what it adds up to. That's pretty cool, okay? And if r is greater than or equal to 1, then this guy diverges, doesn't converge to anything. Okay, now I told you at the beginning of this section that I had to give you some theorems before we could dive into the problems. I'm almost there. I've told you what the geometric series looks like. You're going to have to use that. I've told you, you know, what some other things are in general, how they're working as far as the converging and diverging. I have to give you a couple more theorems, and then I promise we're going to get to the examples right after that, okay? So here's another theorem that you have to know, okay? And these are all useful, so these are things you're going to end up having to memorize. If the limit as n goes to infinity of a sub n doesn't exist, that means it diverges. That's all that means, okay? Or if the limit as n goes to infinity of a n does not equal 0, okay? Then the corresponding series which is the sum from n is equal to 1 to infinity of a sub n is divergent. Okay, that's an important theorem. But when you think about it, it's not all that hard. What it's saying is, remember, this limit here of a sub n, there's no sum in there. That is the limit of the elements of the sequence that obviously you're adding together in your series. If you take the limit, which is what all we did in the last section on sequences, if you take the limit of the numbers of this sequence, and that diverges, in other words, it goes off to infinity, then you have no hope in a prayer of that series converging. Because if you're adding up the infinite number of things, and those things go to infinity, there's no way in heck that that series is going to converge. And that's what it's saying. If the limit of the elements doesn't exist or diverges, okay, then the thing diverges. Or if the limit of the elements doesn't equal 0, then the thing diverges. Because think about it, if you're adding up 1 plus 2 plus 2.1 plus 2.2 plus 2.3, if the elements are going and approaching a limit, even if that limit exists and it's equal to 3, let's say all the elements of the sequence are approaching a number. They're approaching 1, like we actually had a few examples where the elements, the actual numbers of the sequence, are approaching 1. Now, if I try to add an infinite number of things together, okay, and they're approaching the number 3, well, as I start to get close to infinity, I'm going to be adding things pretty close together to 3. I'm going to be adding 2.99999 plus 2.9999999 plus 2.9999999. I'm never going to get anywhere with the summation because I'm going to be adding up things that are otherwise different than 0. I'm never going to get a series that converges if I keep adding things together that are big. Okay? So if the elements of the sequence diverge and go off to infinity, obviously I can't get a summation out of that exists. And if the elements of the sequence converge to anything other than 0, there's no way I can add those things together and get something that converges. Okay? That's all it says. It doesn't say anything about the opposite of this. It doesn't say anything about any other case. It just says the limit of the elements doesn't exist, or if it doesn't converge to 0, then the corresponding series diverges. That's all it says. Now let me give you a corresponding theorem, a very similar theorem. It's related, very related. That's why I'm presenting them together. If the series, which is the sum, by the way, of n is equal to 1 to infinity of a sub n, is convergent, then the limit as n goes to infinity of a sub n is equal to 0. Okay? Let's read that one more time. If the series, which is the summation of all of the elements, actually converges, then we know for sure that the limit of the elements must have approached 0. Because, and you think about it, I've hinted about this all the time. Really, the only way that you're going to have a hope and a prayer of having a series actually converge is if the elements of that sequence that you're adding together get smaller and smaller. That's the only way it's going to happen, okay? Because if they go anything other than smaller and smaller, when you start adding them all up, you're not going to get a number. You're not going to converge to a number when you add them, okay? So that's what this is saying. If the series, when I add these things up, actually does converge, then we know for sure that the elements of the sequence must have approached 0, because there's no way I can get a convergent series that adds up to anything if the elements don't do that, okay? So, like I say, I like to write this down, and that's what you'd see in the book, and I put basically, to kind of show you in layman's terms what that means, basically, if the limit as n goes to infinity of a sub n does not equal 0, then the series over a sub n diverges. Okay? If the limit of the elements in the sequence doesn't approach 0, then the series diverges. Okay? That's what that means. And there's no way you can get a series that converges unless those elements actually approach 0, because you're adding them up. They have to approach 0 in order for you to get anything reasonable. That's the first thing. And then the second thing is, if the limit as n goes to infinity of a sub n does equal 0, so the actual elements do tend towards to go to 0, okay? Then the series may, this is very, very important, or may not converge. Let that sink in. It's very important, okay? And if it converges or not, by the way, is going to be dependent upon how fast they go down to zero, how fast these elements go down to zero. So summarizing this stuff here, basically what it says is, if you take the limits of the elements in the sequence and they approach something other than zero, then you know for sure that the series does not converge. It diverges, because there's no way I can add up things that they get bigger and bigger, or that even if they have a constant value, if I'm adding an infinite number of them up, there's no way I can add and get anything other than infinity out of it. And so if I have the series converge, I know that that must be the case. But if I take the limit of the elements in the sequence and I actually get zero, which means that those elements go down, 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 down as I approach zero, which we've done lots of problems like that, then the series, which is the summation of all of those things, may or may not converge, okay? Now, so far, I've shown you the geometric series that does converge and some other ones that does converge when those terms go down to zero. But you're going to have other series that we're going to talk about here in short order that do not converge, even though the terms approach zero. So what I'm trying to say is, back in the beginning when I gave you that big prelude and I said, look, you can have terms that approach zero, individual elements that approach zero, and I can add them all up, an infinite number of them up, and in some cases it can actually add to a number. So the geometric series was an example of that. Those terms approach zero and that thing does converge. But there are going to be other series where the terms also approach zero, and some of those do not converge, so you really can't tell ahead of time if it's going to converge or not. That's what all this stuff is going to be dealing with, teaching you how to figure that out, okay? But it's a necessary and sufficient condition it's a necessary condition for the terms to go to zero to give you a hope and a prayer of that series converging, but it does not mean that it actually does converge. And we're going to spend quite a bit of time teaching you various methods and tests to figure out if the series converges or not. Okay, now we're going to get to our first problem, okay? We're going to find out if the following series converges, and if so, we're going to find the sum. All right, so the series goes as follows. 4 plus 8 over 5 plus 16 over 25 plus 32 over 125 plus dot, dot, dot. So it goes on and on forever. Now there's got to be some pattern here. First thing I want you to know right away is, look at this. It goes from 4 to 8/5, 16, 25, so on and so on. It looks like the terms, or the elements of the terms in this series approach zero. So I'm adding up things that are getting smaller and smaller and smaller and smaller. And from the last theorem we had on the previous board, that gives us a hope and a prayer of this series converging. It doesn't tell us it does converge, but it tells us we have a shot. Okay, that's what it tells us. So what I'm going to do here is I'm going to write down, this is n is equal to 1, because we want to find out a formula for this series here. So I want to try to find out what that is. N is equal to 3, and n is equal to 4. Okay, so we have a hope and a prayer here. Now, you kind of have to play with this for a while, but what you're going to find is that this can be written as n is equal to 1 off to infinity. Okay, well, what is the first term? What could that be? Okay. This thing can be written as 2 to the n plus 1 over 5 to the n minus 1, okay? Because when you think about it here, if you put n is equal to 1 in here, 1 minus 1 gives you 0, 5 to the 0 gives you 1, so the first term has nothing on the bottom, and on the top it's 2 squared, which is 4. And if you plug in n is equal to 2, you'll have 2 to the third is 8, and you'll have n is equal to 2, 2 minus 1 is 1, so 5 to the first is 5. So this representation is representative of this series. 1 goes to infinity. This is the form here, and I want to find out if this thing converges or not. Okay. Now I haven't given you too many tricks in your tool bag yet this early on to figure that out. We're going to learn in the next several sections all kinds of crazy ways to figure out if these things converge or not, but I haven't gotten there yet. The only thing I've really taught you, other than the conceptual stuff, is the geometric series and when that thing converges. So my advice to you is, especially early on and when you first start studying the series and you just learn about the geometric series, try to beat these things into the form of a geometric series. You know, it kind of looks like a geometric series. I mean, you have 2 to the n plus 1, 5 to the n minus 1. You have powers here, so you know it looks a little bit like a geometric series. So try to beat it in the form of geometric series. By the way, the geometric series, to refresh your memory, looks like sum n is equal to 1 to infinity of a to the r n minus 1. So I need to have a constant times a number raised to the power of n minus 1. So how would I do that? How would I beat this into the shape of this, into the form of this? How would I do that? Okay. Well, let's try. Sum n is equal to 1 to infinity. Okay. How would I do that? Well, on the top, if I say 2 to the n minus 1, okay, and the bottom, if I say 5 to the n minus 1. But in order to make this thing legal, I'm going to have to multiply the top by 2 to the 2 power. Okay? Because look at what I've done here. Just make sure that what I have here is exactly equivalent to this. I want to have powers of n minus 1 because I'm trying to get to this form. So on the bottom, I don't touch it. On the top, I rewrite this as 2 to the n minus 1 times 2 squared. If I were to simplify this, I would say it's 2, and I would add the exponents. 2 to the, and I add this to this, I would get 2 plus 1, which is exactly what I have here. So this numerator is exactly equal to that one. Okay. Now what this does for me though, what it does for me is it lets me write it like this. I can say this is equal to the sum, n is equal to 1 to infinity, 2 squared is 4, okay, and then I'm going to have this fraction here, 2 to the n minus 1 over 5 to the n minus 1, but I can write that as 2 over 5 to the n minus 1, okay. So look, I've completed my transformation. I've taken this seemingly unrelated thing to a geometric series and I've put it in the form of a geometric series. It's a number times a number raised to the power of n minus 1 going from 1 to infinity. Now if you go back to the section on geometric series, it says that for any geometric series, when r, absolute value of r, is less than 1, and it is in this case because that's a fraction, then this series definitely converges. And not only that, it tells you what it converges to. So this series converges to the sum a over 1 minus r. Okay, converges to a over 1 minus r. A is equal to 4, and 1 minus r is 2/5. Okay, so on the top I'm going to have 4, and on the bottom I'm going to have 1. Actually, I'm going to change this. I'm going to write this 1 as 5 over 5 minus 2 over 5 because I actually want to do the subtraction. Okay, so it's going to be equal to 4 over 5 minus 2 is 3 over 5. And then actually taking this bottom fraction, flipping over and multiplying 5 times 4 is 20 over 3. So what we've done is we've found that this series actually does converge, and not only that, because it's a geometric series and because I know what that equals, because I know what a is and I know what r is, it actually converges to a number which is 20 over 3. Okay? So the geometric series is a case when you're actually able to find out what the series converges to, what the number actually is, because it's a special case and they told you in the textbook what this thing converges to. Most of the series that we're going to study as we go on and do the next several sections, we're not going to be able to figure out what it adds up to, we're just going to be able to figure out if it converges or not. Okay? So let's go ahead and do a few more problems. What if you had the sum as n is equal to 1 on up to infinity of 2 times 3/4 raised to the power of n minus 1. Okay, raised to the power of n minus 1. So, question for you here. Remember the form of a geometric series. The geometric series was equal to sum n is equal to 1 on up to infinity of a times r to the n minus 1. Does that look like the form of a geometric series? It surely does. You have a number times some number raised to the power of n minus 1 going up from 1 to infinity. That's a geometric series. A is 1, r is 3/4. Because this guy here, r, is less than 1, okay, then that series converges. Okay, so we know that a is equal to 2, r is equal to 3/4, and precisely because this is less than 1, the absolute value of it's less than 1, we know it converges, and it converges to the sum a over 1 minus r, which is what was given to us in the theorem. A is equal to 2, r is 3/4, so it's 1 minus 3/4, but I actually want to do this simplification, so I'm going to write this as 4 over 4 minus 3/4, okay? And I'm going to actually do that, and I'm going to say that's going to be 2 over 4 minus 3 is 1/4. Taking this fraction, flipping and multiplying, 4 times 2 is 8 over 1 is just 8. So this guy actually converges to the number 8. And it's just because the geometric series is so nice to us and tells us what it converges to that you can actually do that. Okay? So in all of these problems, basically we're going to try to see if they're equal to the geometric series, and if they are, we're going to use that. What if we have sum of n is equal to 1 on up to infinity of 5 times e over 3 to the nth power. Okay? Is that thing a geometric series? Okay? Well, let me ask you this. The geometric series, just to refresh your memory, was sum n is equal to 1 on up to infinity a times r to the n minus 1. That's what the geometric series is. Well, it doesn't look quite the same because I do not have an n minus 1 up here. So what I want to try to do is beat that thing into shape, the shape of a geometric series, and then once I have it in that form, if I can get it to that form, I will know if it converges or not. Okay? So let's do that. I can write this as the sum of n is equal to 1 on up to infinity. So what I'm going to do here is I'm going to say, I want this thing to be in this form. So what I'm going to do is I'm going to write it like that. 5 times e over 3 to the n minus 1. I'm going to say that that's going to be my form. I'm going to say I'm going to have a 5 here just because that comes down, and I'm going to make this exponent equal n minus 1. But in order to do that, I'm going to have to multiply this by something to make it equal to what my original thing was. So what you're going to have to multiply by is e over 3, and you're going to have to pick some power here. And the only power that's going to work is going to be 1. E over 3 to the first power. Now look at this. If I were to simplify this, if I were given this and say simplify, it would be e over 3, and you would add the exponents together, which would give you e to the n. So I take this, I put it in the form of my geometric series, but then I multiply by something to make it work out with what I had. Okay. Now this then equals n is equal to 1 on up to infinity of, this is just a number. E over 3 to the first is just a number, so it's 5e over 3, that is a number, okay, times e over 3 to the n minus 1. Now look at this. This is a, and this is r, okay? So here we know, because this is a geometric series now, we beat it into this form. This is a constant, this is an r to the n minus 1. So we say a is equal to 5e over 3, and r is equal to e over 3. Okay, now e is roughly 2.7. 2.7 over 3 is less than 1. So we do know it converges because r is less than 1. So it converges to a over 1 minus r. A over 1 minus r. A is 5e over 3 over 1 minus r. 1 minus e over 3. So it converges to that. So we'll say that it's 5e over 3 over, simplifying this, 3 over 3 minus e over 3, because I actually want to do that subtraction, and that's going to be equal to 5e over 3 over here, 3 minus e over 3. Okay? Now when I do that, this denominator cancels with this denominator, and so the final answer is going to be equal to 5e over 3 minus e. And that is equal to that. So it's 5e over 3 minus e. So that was a example where I had a series that didn't quite look like a geometric series, but what I do is I say I'm going to try to beat it in that form, so I write it like that, and then I multiply by something to, you know, make it equal to what the problem was that I had. And then from then on, I can move this over here. I have a times r to the n minus 1. Okay, now the next problem is the sum as n goes from 1 to infinity of 3 to the minus n times 8 to the n plus 1. 8 to the n plus 1. Okay, so what I want to do here is I want to look at the terms, and I want to find out, does the series converge or not? Okay, so I'm going to take a look at the terms. I can rewrite this. If I want to find out how these things behave as I go off to infinity to see how these terms behave, I would rewrite it as this. I could say, well, I could say this is going to be on the top 8 to the n plus 1 over 3 to the nth. I just take this and I move it down the denominator, and obviously I'm still taking the sum of n goes from 1 to infinity, okay? And I could say, well, this is going to then be equal to 8. Again, let me go ahead and write my sum down. N is equal to 1 to infinity. On the top, this is going to be 8 to the n times 8 to the first, because I'm just splitting this up, because I'd be adding them if I were trying to simplify, over 3 to the nth power. And if I'm going to split this up further, sum from n is equal to 1 to infinity. This 8 is just a constant, 8 times, and this is 8 to the n over 3 to the n, so it's 8 thirds to the nth power. So that is my series here, okay? Now, it's not quite in the form of a geometric series, but if you look back, just a few minutes ago when we talked about this, It's the same sort of deal. You have a number times something to the nth power. This is a number greater than 1. 8/3 is a number greater than 1. So since you're taking powers of it, as you go on and on, higher and higher and higher, the elements that you're adding together are going to be bigger and bigger and bigger. And so that means because the elements in the sequence diverge by one of those theorems that we had, the series diverges, okay? So we say since 8/3 is greater than 1, each term is larger than the last. Okay, each term is definitely larger than the last term that came right before it, so that we basically say, to be consistent with the theorem, the limit as n goes to infinity of the elements in the sequence equals infinity, and so the series diverges by that theorem. So by that theorem, the series diverges. Okay, we looked at the elements. We proved to ourselves that the elements themselves got bigger and bigger and bigger, going off to infinity. And when you add those up, there's no way it's going to converge, so we say it diverges, okay? What if you had the sum of n is equal to 1 on up to infinity of -2 to the n plus 3 over 5 to the n minus 2? Okay? Again, I have powers on the top and powers on the bottom. I think I might be able to get into the form of a geometric series, so I'm going to give it a shot. The geometric series, for your reference, is the sum n is equal to 1 to infinity of a times r to the n minus 1. So I'm going to try to beat it in that form there. Okay, I'm going to try to beat it in that form there. So how am I going to do that? Basically, I'm going to rewrite this, and I'm going to say I have the sum n is equal to 1 to infinity. First, you have to assume that you can beat it in that form, so I'm going to do that. I'm going to say, well, I'm going to write this on the top as -2 to the n minus 1, and on the bottom I'm going to say it's 5 to the n minus 1. I'm going to assume I can write it that way. What would I have to multiply by on the top and on the bottom to get it to equal what I actually had to begin with? Well, I would have to multiply this by -2 to the 4th power, because 4 plus -1 gives me 3. If you simplify this, you're going to get this back. On the bottom, I would have to multiply by 5 to the -1. 5 to the -1. Because if I were to try to simplify this, 1 plus -1 minus 1 gives me my -2. And that's exactly that. Okay? So, if I were to take this, this looks like it's shaping up to be a constant, and this looks like it's shaping up to be in the form of a geometric series. Okay, now continuing on, this is going to be simplifying. N is equal to 1 on up to infinity. Now, this is just a number, okay? So this is -2 to the 4th, and you have -5 there. So what would I do here? What is -2 to the 4th power? Well, that's going to be positive 16, so I'm going to have 16 times 5 to the -1. That's going to be moved upstairs, so that's going to be times 5. Okay, so 16 times 5, that's my constant here, times. And then this is -2 to the n minus 1 over 5 to the n minus 1, so I could write that as -2/5 to the n minus 1, all inside of that parentheses there. I'm just taking this and sticking it inside one parentheses and having a common exponent. So this looks exactly like a geometric series. I have a constant and I have an r n minus 1. And by the way, we know it converges because r is -2/5, and we say as long as r is between -1 and +1, the thing is going to converge because the terms are going to go down to 0. Okay? So this is going to equal, n is equal to 1 to infinity. 16 times 5 you're going to find is 80. And then you have -2/5 to the n minus 1. Okay? So you know this thing is going to converge. So you say it converges because it's a geometric series. Okay? And you know that a is equal to 80 and r is equal to -2/5. And it converges to the value of a over 1 minus r. So this is going to be 80 over 1 minus r, but r is -2/5. Okay? So what I'm going to have in the end is 80 over, I'm going to write this as 5 over 5 because I'm going to actually want to do this math, plus 2 over 5. So it's going to be equal 80 over 5 plus 2 is 7/5. And now when I take this guy and flip it up over here, I'm going to get 400 over 7. And that is the answer, 400 over 7. So I was given a function that looked kind of like a geometric series, okay? I assume that I can write it that way, so I I write it as negative 2 to the n minus 1, 5 to the n minus 1, because that's the form, and then I modify it by multiplying by whatever I have to multiply to get it to equal what I had. Okay, I reduced this down to a number which was 80, and then I had the negative 2/5 inside to the n minus 1. I knew it converged from the theorem, and I just applied the theorem to tell me what it converged to. Okay, the final problem in this section is, what if I have the sum of n is equal to 1 to infinity of n over n plus 1? Okay, now obviously it's not a geometric series. It looks nothing like the form of a geometric series. So let's go ahead and examine the terms and figure out what these terms do. Maybe we can learn something about the terms. So we're adding up these terms. Each term, or each element of the sequence of terms that we're adding up, is given by this. So let's take the limit as n goes to infinity of the terms, which is n over n plus 1, because I want to see if those terms diverge or not. It's going to tell us a lot about what the series does based on the theorems we had before. So this is obviously going to be infinity over infinity, so we have to use L'Hopital's rule. So let's take the derivative. It's going to be limit as n goes to infinity of the derivative of n is 1. The derivative of n plus 1 is 1. Okay, so this thing is going to converge to 1, because a limit of a constant is just going to be whatever that equals to. So these terms, per the theorem before, the terms, which are these things here that we were looking at, the terms, as you take the limit, do not approach 0. They do not approach 0. And if you look back to the theorem, and if you also just think about what a series is, it means that the series diverges. Okay? Because even though the actual elements that we're adding together, if we look at how they behave, they approach the number 1. As I go bigger and bigger, adding them more and more and more and more and more elements together, I'm adding up, as I get way out in the weeds, out towards infinity, I'm adding up a bunch of 1s, because we're saying the elements approach 1. So I keep adding 1 to the previous partial sum. I'm going to get bigger and bigger and bigger and bigger values of that partial sum. I'm never going to get anywhere. I'm never going to converge that series. So we've made great headway in this section, talking about the introduction to series, which are just simply the sum of the set of elements in the sequence. Okay, so we have that as a general definition. We have the partial sums, which are just adding up more and more and more and more of those elements in the sequence, and we look at how those partial sums behave, and that's going to tell us if that sum converges or not.